Okay, so let's talk about specific heat and calorimetry. So before we get to specific heat, we need to talk about heat capacity, which is usually denoted with a big C. And please don't confuse that with kilocalories. That's a different quantity. But this is the amount of energy it's going to take to raise the energy of some substance or some sample by 1 degree Celsius. So if I have a block of metal, basically I want to know how much heating do I have to do, how much energy has to transfer into this object in order to raise it 1 degree, to have a temperature change of 1 degree Celsius. Now the thing is that if I have, say this is iron, and I get some value here for Q, whatever it may be, some X joules. Well, then I take this and I have a big, huge piece of iron. Something like this. Then this clearly is going to take a lot more energy to do the same amount, to have that same temperature change of 1 degree Celsius. Because for heat capacity, it's defined as Q is big C delta T. So the temperature change is the amount of energy is proportional to the temperature change, but it's dependent upon this constant, and that's going to change between these two objects because I have a different amount of mass. And so what we want to do is we want to think about, well, how much is it going to take for just a little defined piece of this thing? So if I had like just a little piece, how much would that take? So this energy is going to go into this little block. And so if we divide this by the mass of the object, I should have done a little m, then we can redefine this. So we'll have Q over m is equal to little c delta T. I'm just dividing the energy into all of these little pieces of this material, and that leads us to specific heat, which is going to be Q mc delta T. So this is a unit per unit mass. So specific heat is defined as the heat capacity per unit mass, or the amount of energy to raise 1 kilogram or 1 gram sometimes, but we'll say 1 kilogram by 1 degree Celsius for a material. And by doing this, we define this quantity right here, that's the specific heat. And it's specific in terms of material, not mass. Terms of material. Now we add mass in there as a multiplier, but it's this quantity right here that really defines it and is dependent upon the material. So what we have is like this before was big C, the heat capacity. So if I have a lot of mass, I'm going to get a larger heat capacity. It can hold a lot more energy through heating. And this is what we're going to be dealing with. So our heat, I guess we could just say, is going to be mc delta T. And since this is a transfer of energy, this is also going to be our change in internal energy, would be our heating, through heating. Now keep in mind there's other ways to change the internal energy, but for right now we're just kind of specifying that we're talking about heating. So here's a table that lists some specific heats for different materials. And notice there's 2 columns. So one of these, I need to change colors. One of these is in joules per kilogram degree Celsius. The other one is in kilocals, kilograms degree Celsius. And remember, a kilocal from the last video is 1,000 calories, or 1 big C, a food calorie. And so what we can see, I'll just look over here, you can see there's some small numbers like lead. Lead is 128, so it doesn't take a lot of energy to raise the temperature of it. Where's another small one? Gold. Where's iron? 452. So a piece of iron, you put it out in the sun, the temperature rises pretty quickly. Or it doesn't take much energy to get it up to temperature. it's gonna, yeah, so it rises fast, but then it'll stabilize, reach equilibrium. Whereas when we look at water, 4186, so we're looking at nearly 10 times as much energy to raise it 1 degree of water, 1 degree of Celsius. Over in kilocalories, you'll notice that's 1 kilocal, because 1 kilocal is equal to 4186 joules, and that comes from the definitions. So anyway, large C, lots of energy. Large C, large specific heat means lots of energy required. So we can use all of this for a process called calorimetry. And what this does is it's the way that we can determine the specific heat for an unknown object. So if we have an object and we know the mass and we raise it to a certain temperature, that we can then put it into water, and from that we can determine the specific heat, because the heat flow will go from hot to cold, because heat always flows from hot to cold, and whatever Q is lost here is gained here. And so the total, because this is isolated, there's no energy that can get out of here. The total energy, so the Q from I'm just going to say hot, plus Q cold equals 0. And if I move that over, then I'll get Q, the heating from the hot one is negative of the cold. So they're opposite, and that makes sense. Whatever I'm losing here, we're gaining over here. And now we can use our specific heat. So this is the water side, and then we have some sample. I'm just going to put S. And so now we can use our specific heat. So the mass, they're using X. So the mass of X times C of X times delta T is equal to negative mass of the water, the C of water, times delta T of the water. Let me do this is of X. Now you got to be careful with this, because you're going to be tempted to just cancel these two terms, but that's not true. The temperature changes will not be the same all the time. Sometimes they will, but not always. So be very careful. This is a big pitfall. So we get mx Cx times the change in temperature of X would be Tx final minus Tx naught equals negative mass of the water, C of the water, times temperature of the water final minus temperature of the water initial. And then from here we can then solve for our unknown. So this is kind of the basis of calorimetry. Now when you go through this, we do have we do have quantities that are the same. So be careful. These are not the same, but this one and this one are. So the temperature XF is equal to the temperature of the water final. That's because of equilibrium. They'll reach thermal equilibrium, so the final temperatures will be the same. But you have to distribute and do all of this stuff. But this is the basics of calorimetry. Heat flows out and goes in, and so we can set it up. This is another one. Don't forget negative. Your negatives. All right. Let's look at a problem, and then we're done. So, cowboy fired a silver bullet with a muzzle speed of 200 meters per second into the pine wall of a saloon. Assume all of the internal energy generated by the impact remains in the bullet. That means that it's kind of an isolated system. What's the temperature change? Okay, so this one we're going to have, our total, it starts with some kinetic energy. And then we're going to have it change into, we're going to have change in kinetic energy plus the change in internal energy. is equal to 0. So conservation of energy. There's no energy leaking out. The system is the bullet. It starts with some kinetic energy, so it flies into a wall, and then it stops. So the kinetic energy goes to 0, and all of it goes into internal energy. Okay, so let's see, we can move one of these over. So delta, our change in kinetic energy is negative delta U internal. So this would be our final kinetic energy minus the initial kinetic energy equals, the only internal energy that we care about is going to be through heating. And so I'll just say that that's going to be negative. It starts with 0. Or here we can do U final minus U initial. Now the U initial, we're assuming that there's none to begin with. So that would cancel. And then over here, the final kinetic energy is 0, so that's gone. And then I have a negative on both sides, so I end up with the initial kinetic energy is equal to the final internal energy. And the final internal energy, it's being transferred from kinetic into internal energy through heating. And Q, or here, let's just write it out. So my initial kinetic energy is equal to the heating done on the object. And heating is equal to mc delta T. So we don't have mass, but that doesn't matter because kinetic energy is 1/2 mv squared is equal to mc delta T. The masses cancel. So delta T I'll divide by C. So I get V squared over 2C. And that's my change in temperature. So now you would just plug in your values. So 200 squared divided by 2 times C is 234 joules per kilogram degree Celsius. So anyway, that's dealing with it. This is a little bit, this isn't a, just straight up like a calorimetry problem, but you can see that any change in internal energy, we can now then tie in our heating, because that's all that we're able to deal with right now. So this MC delta T is what we'll be using.